Hey guys, how you doing? This is Mr. Lee. This is your lecture on 10.3. So in 10.1, we talked about the basics of statistical inference. We also talked about the basics of constructing a confidence interval. In 10.2, we looked specifically at how to construct a confidence interval for a population mean mu. Okay, and that involved if you knew sigma, if you knew the true standard deviation of the entire population, you would just use the z model or the z distribution, right? But if you didn't know, in most cases, you're not going to know. If you don't know what mu is, you probably also don't know what the spread of mu is or the spread of the population is. So you probably don't know what the true sigma is. So in that case, we used Sx instead of sigma, and that introduced more variability or more error because Sx is the sample standard deviation. And while that is a good estimator of sigma, the true population standard deviation, we don't expect it to be exact, right? So we know that there's going to be some standard error. So that distribution is no longer the distribution of z's, but that is the distribution of t's, or the student's t distribution. The big thing with the student's t distribution is that is only for means. Okay, we're not going to be using the student's t for proportions. Okay, that's only for means. And you also learned about degrees of freedom, which for AP Stats, we just use n-1 for the degrees of freedom for which t distribution to use. That brings us to today's lesson on 10.3. Now we're going to construct a confidence interval for a population proportion p, the true population proportion p. Some books call it pi. Okay. Remember this, write this in your notes. We do not use the student's t for P, for population proportion P. We only use the student's t distribution for mu. Okay. For P, we're just going to use the z distribution. So here we go. So there's three things you're going to be able to do. You're going to be able to construct and interpret in context. Okay. And this goes back to 10.1, interpret and construct and interpret a confidence interval for a population proportion P. You're also going to be able to determine the sample size N, which that's just like straight up algebra 1 stuff. You're just going to rearrange the formula for margin of error and basically just solve it for N, okay, which you've already done that plenty of times in 10.1 and 10.2. Sorry. You're also going to describe how the margin of error of a confidence interval changes with the sample size and the level of confidence, capital C. Okay. So right now, before we get started, go back to your notes from 10.1, and there's two phrases I asked you to memorize. One was interpreting a confidence level, C, and I said that's not as important, right? But that was something along the lines of go back to your notes and see if you can find that. But the most important thing, I said this is super important, like burn this on your brain, is interpreting a confidence interval. Okay, that, go back to your 10.1 notes right now and make sure that you have that in your notes, okay, because you have to be able to do that, okay? The phrase I asked you to memorize should say something like, we are 95% confident that the interval from lower bound to upper bound captures the true population, in this case, proportion of whatever in context, right? So let's say that our context was, we want to know out of all the high school seniors in the Tri-Valley area, what proportion of them wears glasses, right? So then our interpretation would be, let's say that our confidence level is given as 95%. We are 95% confident that the interval from blank, lower bound to blank upper bound captures the true population proportion P of high school seniors in the Tri-Valley area that wear glasses. So that's how you contextualize your interpretation. Okay. So if we were in real life, I have this huge jar of beads. I actually do have a huge jar of beads. Some of them are red, but they're all different colors. There's black, green, white, yellow, orange, all sorts of different colors. Okay, and we want to know what proportion of the beads in the teacher's jar are red. Okay, so we're defining a success as red, and anything that's not red, we're defining that as a not success or as a failure. Okay, so you would form teams, about 10 teams per class. Okay, and you would get each team would get a little Dixie cup. Okay, and then you would shake up this jar of red beads, and you would figure out between your team, how would you get a valid SRS? Okay, and some of you might just say, oh, just pour some of the beads into, from the jar into the Dixie cup. And a big debate would emerge, a class-wide debate would emerge, is that or is that not an SRS? Some people would say, well, yeah, of course, because we shook up the jar, we poured some out, that's an SRS. Some people would say, no, that's not an SRS because the beads and the grouping of beads at the bottom of the jar has very little probability of being selected, so it's not really truly random. Okay. But anyways, let's say you go ahead and figure out how to create an SRS. Each team collects an SRS. You determine a point estimate for P, okay, which is just going to be your P hat. And then each team is going to construct a 90% confidence interval for P based on their point estimate. So everyone's point estimate is going to be probably slightly different, right? And then that means that everyone's confidence interval is going to be slightly different. Okay, and then you could go around and compare your confidence interval with everyone else's, and it'd be a lot of fun. Okay, obviously we can't do that, but here's how you would do that. So conditions. Okay, so let's say that your P hat was, you got X over N, right? X is your count of successes or your number of, let's say you get 107 red beads out of your sample size of 251 in your Dixie cup. Okay, so that is a P hat of 0.426. So that is your P hat, that is your estimate, that's your point estimate. Okay, but then you have to do plus or minus your margin of error, right? So to create this confidence interval, to construct a confidence interval, you really need to check your three conditions R and I. Random. Was the sample randomly selected? Yes, you created an SRS. Normal. Does this meet the normal condition? Some of you say yes, some of you say no. Here's the problem. We don't know that the beads in the jar, the entire population is normally distributed. We do not know that. Okay. So we have to check NP and NQ. The problem with checking NP and NQ is we don't know P and we don't know Q. That's the whole point of why we're doing constructing confidence interval. So now what are we supposed to do? I'll tell you in just a moment. Let's go to the next condition, the independence condition. Let's say that I tell you that there's 3,000 beads in the jar. Okay. Do we meet the independence condition? Well, technically, no. I mean, this is not independent sampling, right? This is not independent from sample to sample. We're sampling without replacement. So how do we meet the independence condition? The 10% condition. Okay. Is little n 251 times 10, so 2,510, is that less than or equal to capital N, which is 3,000? Yes, it is. So we're going to meet that condition. Okay. All right. So assuming that all the conditions are met, what is the mean of the sampling distribution of P hat? Well, that's just the true population proportion P. What is the standard deviation of the sampling distribution of P hat? That would be, we learned in section 10.1 that that is root PQ over N. Okay. Here's the problem. We don't know what P is. We don't know what Q is. If we knew P, we wouldn't need to estimate it, right? So here's the deal. In large samples, P hat will be close to P. So instead, okay, we're going to use P hat in checking the normal condition. Okay. So we're going to use P hat. So NP hat is 107 and NQ hat. So we had 107 red beads or successes. We had 144 non-red beads or failures. Both of those are greater than 10. We're going to be okay with a normal condition. Okay. Okay, so how do we construct a confidence interval? Again, we don't know what P and Q are, otherwise we wouldn't be doing this, right? So we're going to use P hat and Q hat. So just like in 10.2, when we didn't know what the true population standard deviation sigma was, So we couldn't use sigma over root n in the last section where we're chasing a mu. We could not use sigma over root n. So what did we use instead of sigma? We used SX, sample standard deviation, right? But when you're using SX, that's the standard deviation of your sample. Is that going to be exactly equal to the standard deviation of the population? No, we know it's not. So you're introducing more error. So SX over root n in last section, that was called the standard error, not the standard deviation of the statistic, but the standard error. Likewise, in today's section, 10.3, okay, we don't know what P is, okay? So therefore, we don't know what the standard deviation of the sampling distribution of P hat is. What we do know is what P hat is. So we use P hat times Q hat in this expression. And so instead of standard deviation, we call this the standard error of the sample proportion. So when the standard deviation of a statistic is estimated, then that result is called the standard error. Okay. If the normal condition is met, we can use a normal curve to find a level C confidence interval. So this is just finding the Z stars, okay, which if you're not sure on how to find the Z stars, you can go back to my 10.1 lecture. But real basically, if we're using a 95% confidence interval, so 95 is our confidence level. So in the standard normal, we know that this interval captures 95% of the density or 95% of the area under the curve. Okay, and so all we need to know is what is this critical value right here? What is the positive critical value that correlates to a 95% interval? Well, when you have this 95% of the area here, you have 5% of the data is left in these right tail and this left tail. So it's equally distributed. So this is 2.5%, that's 2.5%. When you're calculating this critical value, what you're calculating in your calculator is inverse norm. So second vars inverse norm, 0.975, not 0.95, because you're calculating a left tail. So you have the 0.95 plus the 0.025. So this is inverse norm, 0.975, enter, 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 okay, and you get 1.96 as your critical value. That I told you to memorize. So memorize the Z star for 95% and memorize the Z star for 90%. So memorize 1.96 and 1.645. Every other confidence level, you can just use inverse norm. Okay, so like if the test tells you, hey, construct a 78% confidence interval, or hey, construct an 80% confidence interval, you would know how to use inverse norm just to find the critical values or the Z stars that correlate to whatever confidence level you're using. Okay, so let's move on. Okay. Oh, you can also use the table. Okay, that's how you'd use the table. Okay, real fun. Not going to use the table. Okay, so here we go. So we have statistic plus or minus critical value times standard deviation of the statistic. In this case, we're going to use the standard error because that's all we have. Okay, so let's go ahead and do this. Here it is right here. So your statistic, your p hat was 0.426, okay, because that was your statistic. That was your sample proportion. Plus or minus your z star. For a 90% confidence interval, we're using 1.645. And then under the radical, you have p hat, q hat over n. So p hat was 0.426. Q hat is just the complement, or 1 minus that. And then n is obviously your sample size. So you're going to simplify this margin of error on the right side of the plus or minus. That's where you get 0.426 plus or minus a margin of error of 0.051. And then that is a valid way to express a confidence interval. But the more common way, and the way that I want you to get used to doing it, is in parentheses, your lower bound, comma, your upper bound. And that's just where you do the work of 0.426 minus 0.051, which equals 0.375, and 0.426 plus 0.051, which gives you the 0.477. Here's the big part. Go ahead and interpret that interval in context of the problem. Please go ahead. Pause the video and see if you can do that. Okay, unpausing the video. We are 90% confident that the interval from 0.375 to 0.477 captures the true proportion P of red beads in Mr. Lee's jar. So this range gives us a range of, this interval gives us a range of plausible values for P. Now, if Mr. Lee says, oh, I think 50% of the beads are red, okay, notice how that claim, Mr. Lee's claim of 50%, is outside of the entire interval. Now, we trust our interval because we followed the procedures, right? So do we trust that claim that 50% of the beads are red? No, this gives us reason to doubt the claim that 50% is the true population proportion P, because 50% is outside of the entire interval, right? The upper bound of 0.477 is not, it's lower than 0.5. So we doubt the claim. So anytime you're doing inference, whether it's a confidence interval, whether it's a significance test, you are going to follow the state plan do conclude process. Sounds like a lot of work. It's actually not bad. If you don't follow the process, you're not doing inference properly. Okay. So state is just what parameter do you want to estimate and at what confidence level. Okay. So we wish to estimate the true population proportion P of red beads in Mr. Lee's jar at the 90% confidence level. Plan, you're going to check your conditions and you're going to identify the appropriate inference method. Now, you're going to learn lots of different inference methods. You've already learned 3. Okay, what are the 3 different inference methods you learned? What are the names of them? Go ahead and turn on your calculator if you're not sure. Or even if you are sure, go ahead and turn on your calculator, your trusty TI-84. Go to Stat, scroll over to Tests. Okay, what do you see? Number 1 is a z-test. We haven't learned any tests yet. Test means significance test or hypothesis test. We're going to do that for the rest of the course. After chapter 10, it's all tests. Okay, but we haven't learned the z-test yet. But the z-test will be basically a one sample significance test for mu. T-test, number 2, haven't learned that yet either. Same thing, that's going to be for mu. 3 and 4 are 2 sample z-test and 2 sample t-test. Haven't learned that yet either. Those are for mu. 5 and 6, 1 proportion z-test, 2 proportion z-test. Those are your significance tests for proportions for P. Here we go, number 7, z-interval. Great, that sounds familiar. We've done a z-interval. Is that what we just did in section 10.3? Is that an interval for P? Think about that, yes or no? Is that an interval for P? No, it's not. Z-interval is your one sample confidence interval, okay, using the Z distribution for mu. Okay, that's what the very first thing we learned in 10.2. Well, when do we use Z interval for mu? We use that when we know sigma, which is not very often. Scroll down. Number 8. T interval is what you use most commonly to create or construct a confidence interval for mu. Okay, that, again, you need the degrees of freedom. That one, you don't know sigma. So instead of using sigma over root n, you're using Sx over root n, which is the standard error. Okay. Number 9, 2 sample Z interval. Haven't learned that yet. Again, that's for mu. Number 10 or 0, 2 sample T interval. Haven't learned that yet. That's for mu. Number A, That is what we're doing today. A one proportion. So it's one proportion. You're only given one proportion because you only had one sample. It's a one proportion Z interval. Notice it says proportion. So obviously that is inference for P. Scroll down to B, two proportions in. Same thing as what we did today, only slightly different. We're looking at the difference between two p-hats. C, that's your chi-square test. We're going to do that later in the year. D, chi-square goodness of fit test. We're going to do that later in the year. AP Bio students, you've already done this. E, two sample F test. You're going to do that in college. We're not going to do that in AP Stats. F, Lin-Reg t-test. Yes, we're going to do that. That is a t-test, okay, to tell whether about linear regression, okay. G, linear regression t-interval. Yes, we're going to construct intervals for linear regression. A or H, ANOVA. That's analysis of variance. You're going to do that in college, and that's all you have, okay. So what's the big thing to remember? Don't get confused between 7, which is a Z interval, and A, which is a one prop Z interval. This, for P, what we did right now is A, okay, is a one proportion Z interval. That is the appropriate inference method. So for plan, the sentence you're going to write for this is, we will construct a one sample Z interval, or we will construct a one proportion Z interval. Either one of those works. It doesn't matter what you call it. Just one proportion or one sample, but it's a Z interval for P. Okay, check conditions. That's where you literally write out the words random, normal, and independent, and write a sentence for each one of those. Okay, do. That's where you do these calculations right here. This is the do right here. Okay, that's where you show the calculations. Okay. And then conclude is where you actually write the sentence. We are 90% confident that the interval from lower bound to upper bound, put whatever those numbers are, captures the true population proportion of red beads in Mr. Lee's jar. Make sure you contextualize your conclusion. So that's all we have for constructing a confidence interval. The rest of this lecture is on algebra. Okay, how do you choose a sample size? Basically, they will give you a margin of error, and you just set that margin of error equal to whatever they give you, like 2% or 5% or 3%, and then you just solve for n. Okay, here's the problem. If they give you a p-hat, you'll use the p-hat and the q-hat. If they don't give you a p and they don't give you a p-hat, then the widest margin of error would be when p-hat and q-hat are 0.5. So just plug in 0.5 times 0.5. Okay, that'll give you the best margin of error, or the widest margin of error, I should say. Okay, so if they don't give you a p and they don't give you a p-hat, use 0.5 and 0.5. The other thing, the final thing is you want to round up. Okay, here we wanted our margin of error to be 3%. So estimate P within 0.03. So within means plus or minus. So that's your margin of error. Okay, so there's your 0.03. There's your 95% confidence. There's your 1.96. That is your Z star for 95%. Okay, now you solve and you get n equals 1067.11. Should you round down or round up? You're always going to round up. Okay, if you round down, you're rounding in the wrong direction, right? Because you want to be on the conservative side. So you're going to round this thing up to 1068. And this is just the algebra. I'm not going to walk you through the algebra. It's just solving for n. Guys, that's all we have. Make sure that you know the state plan do conclude. You might want to take a picture of that or write that in your notes. Have a great day, and I'll see you in the next lecture.